Hi there. So today we're going to be doing a few more examples on the integration of rational functions. Okay, so I've got two examples here just to illustrate the process again. Okay, so the first example, number one, is the integral of x to the 4 minus 2x squared plus 4x plus 1. Okay, so that's our numerator, all divided by x cubed minus x squared plus, minus x, and then plus 1. Okay, so we would like to integrate this rational function. Now remember, step one was to look at the numerator and the denominator and make sure that the numerator has degree less than the degree of the denominator. So here we see the degree of the numerator is 4, and then the degree of the denominator is 3. Okay, so that means the degree of the numerator is bigger. So before we get to the integration, we need to do the polynomial long division. Okay, to make sure that the numerator has a lower degree than the denominator. So let's do that first. So we're going to take our numerator, x to the 4 minus 2x squared plus 4x plus 1. Okay, so that's a fourth degree polynomial, and we're dividing by this cubic polynomial. X cubed minus x squared minus x plus 1. Okay, so we need to divide. So how many times does x cubed go into x to the 4? It's going to be x times, because x times x cubed, that's going to give us x to the 4. So we multiply down, and then the result is going to be x to the 4 minus x squared, minus x cubed, and then minus x squared plus x, and then we have a 0 at the end there. Okay, now we need to subtract these. So x to the 4 minus x to the 4, that's going to be 0. Minus 2x squared. In the numerator, we don't have an x cubed, so there's like an invisible 0 there. So we have 0 minus x cubed, so that's going to be a plus x cubed. Okay, now we can look at the squared term. Minus 2x squared minus x squared, so that's a plus x squared. We have a minus x squared there. And then 4x minus x, so that's going to be plus 3x. And then the 1 minus 0, that's just going to be plus 1. Okay, so now we do the next division. We have this x cubed divided by x cubed. That's just going to be a 1. It goes in once. And then we multiply down the 1. Okay, so we're going to end up with x cubed minus x squared minus x, and then plus 1. Okay, we need to subtract these two now. So x cubed minus x cubed, that's going to be 0. Minus x squared minus x squared, so that's a plus x squared. That's just going to be a 0. Then 3x minus x, that's the same as plus x, so it's going to be plus 4x. And then 1 minus 1, that's just going to give us 0. Okay, so then this bottom term here, this is our remainder. Okay, or the remainder after division. So in fact, our rational function, the x to the 4 minus 2x squared plus 4x plus 1, if we divide this by x cubed minus x squared minus x plus 1, we're going to be left with this whole part, like I said in the previous lecture. So that's x plus 1, plus that fractional part or that remainder part that we usually get when we're dividing numbers, but here we're dividing polynomials. So this fractional part or the remainder part will then be 4x over x cubed minus x squared minus x plus 1. Okay, so that would be your fractional part if this was just number division. Okay, so now we can see that the degree of the numerator is less than the degree of the denominator for this remainder part, which is good. That's what we wanted. So now we can carry on with the partial fraction step. Okay, so instead of integrating this first part, we can integrate this next bit. So x plus 1 plus 4x over x cubed minus x squared minus x plus 1. Okay, so that's just the pre-step that we needed to do. Now, the first step of the partial fractions is to look at the denominator and try and factorize it as much as possible. So this term here, this cubic, we now need to factor that. Okay, but that's not too difficult. This is going to be equal to the integral x plus 1 plus 4x over, and if we factor that, we're going to get x minus 1 squared times x plus 1. Okay, so that's if we factor the denominator there. And then you can just expand that out just to check that that's right. dx. Okay, so we've got two factors that we need to deal with. We've got this x minus 1 squared, and notice how it's repeated because of the square. And then the second factor is x plus 1. So we would like to decompose the single fraction into two parts. So let's just do that on the side here. So we've got 4x over x minus 1 squared, it's repeated, times x plus 1. We want to split it up. So we're going to have three terms, okay, because the x minus 1 is repeated, so that counts as 2. And then we have the x plus 1. So this is going to be some number a over x minus 1. But since it's repeated twice, we need to add an extra term for the squared. So it's going to be plus b over x minus 1 squared. And then for the third term, it's just c over x plus 1. That's not repeated, so we just have one term for that. Okay, so now we need to figure out what is this a, b, and c values. So what we can do is multiply through by the denominator just to clear that. And then we will get a single nice polynomial with the values of a, b, and c. So let's do that. So we're going to have 4x is equal to, if we multiply through by x minus 1 squared times x plus 1, we're going to get a times x minus 1, because one of the x minus 1s in the denominator get cancelled, and then we have the x plus 1. Plus b, the denominator of the b term is x minus 1 squared, so that cancels. So we're just left with an x plus 1. And finally, for c, the denominator of c is x plus 1, so that gets cancelled when we multiply through. So we're just left with the x minus 1 squared. Okay, so we're left with this. So what we can do now is generate three equations by letting x take on several values. So first, we can let x be 1, because in that case, the a term is going to vanish and the c term is going to vanish. So if we let x be equal to 1, we're going to get 4 is equal to, the a term vanishes, we get 2b, and then the c term vanishes. Okay, so this gives us b is equal to 2. Next, we can let x be minus 1. Now, if x is minus 1, the a term vanishes and the b term also vanishes, and we're just left with the c term. So we're going to have minus 4 is equal to 4 times c. So in this case, c is equal to minus 1. Okay, so now we just need to solve for the a term. If we let x be 0, then we're going to have 0 is equal to, we're going to have minus a, then plus b, and plus c. Okay, so that's just letting x be 0. But we know the values of b and c, so we can substitute that in, and then we can get our value of a. Okay, so subbing in, we get a is 1. Okay, so we've got our a term, we've got our b term, and we've got our c term, which means we can finally write out this partial fractions here. So this is going to be equal to the integral x plus 1 plus the a term of, the value of a over x minus 1, but a is 1, so it's just 1 over x minus 1, plus the value of b, which is 2, so it's going to be 2 over x minus 1 squared, plus c, that was minus 1, so it's minus 1 over x plus 1 dx. Okay, so we've successfully split up our fraction into the 3 terms corresponding to the 3 terms being multiplied in that denominator. Okay, so what we need to do now is look at all of the terms and then integrate. Okay, but that's quite easy to do. The integral of x is just 1/2 x squared. The integral of 1, that's just x. The integral of 1 over x minus 1, that's going to be plus the natural log of x minus 1. Remember your absolute values. The integral of 2 over x minus 1 squared, that's just going to be minus 2 over x minus 1. And lastly, the integral of 1 over x plus 1 is natural log of x plus 1, but we've got the minus sign. So minus the natural log of x plus 1. And we need our constant c, so plus c. Okay, now just one more thing. We've got this natural log and this natural log. If you wanted to, we could combine them into one natural log using our natural log properties. So just to show on the side here, the natural log of x minus 1 over x plus 1, we could have written, so if we expand this out, we get natural log of x minus 1 minus the natural log of x plus 1. Okay, so we could have combined them if we wanted to, or you can leave them separate. It doesn't matter, same answer. Okay, so that was the first example. Just note that you may need to do your polynomial long division before you get to your partial fraction steps. Okay, so it's like a step 0 kind of thing. Okay, and then you go on to your partial fraction steps from there. Okay, let's take a look at the next example, example 2. Okay, so here we have the integral of 2x squared minus x plus 4 all over x cubed plus 4x dx. Okay, so we want to figure this one out. Now remember, we need to check degree of the numerator needs to be less than the degree of the denominator. Quick check here. We've got a 2 for the numerator, 3 for the denominator. So that's fine. We don't need to do the long division. Okay, so we can go right into step 1, which is splitting them up. So we have the integral of 2x squared minus x plus 4. We need to factorize the denominator so we know how to split things up. In this case, we can just take out an x, and we're left with x squared plus 2. X squared plus 4 dx. Okay, so this gives us our 2 factors for the denominator. And notice that the second factor is quadratic, and we can't simplify it anymore. It's not like x squared minus 4, where we could then simplify it. Okay, so we stuck with it being quadratic. Okay, so let's split this up. So we're going to have a over x plus, now since it's quadratic, the numerator is going to be linear. instead of just a constant. So it's not going to just be b over x squared plus 4. It's going to be bx plus c. We need a linear term at the top. Okay, over x squared plus 4. Okay, so just keep that in mind. If the denominator is a quadratic, which you can't simplify anymore, the numerator has to be linear. And if the denominator was a cubic that you can't simplify anymore or factorize anymore, then the numerator will have to be a quadratic. Okay, so please just keep that in mind. Okay, so we need to find a, b, and c now. So originally, we had 2x squared minus x plus 4 all over x times x squared plus 4. And that's equal to a over x plus bx plus c over x squared plus 4. Okay, we can multiply through by this denominator on the left-hand side just to clear that. So we're going to have 2x squared minus x plus 4. That's equal to a times x squared. Sorry, let's rewrite that. A times x squared plus 4 plus x times bx plus c. Okay, so this is easier to work with than the fractions. Okay, so what we can do now is either choose different values of x, like we did last time, and then solve for a, b, and c, or what we're going to do this time is multiply the right-hand side out and then compare coefficients. So we're going to have 2x squared minus x plus 4 is equal to ax squared plus 4a plus bx squared plus cx. So we have 2x squared minus x plus 4 is equal to a plus b x squared plus cx plus 4a. Now we can just look at each of the terms individually, there and there, and then there and there, and they should match up. Okay, so if one polynomial is equal to another polynomial, then the coefficients better be the same as well. So here we're going to get a plus b is equal to 2, c is equal to minus 1, and 4a is equal to 4. Okay, so not too difficult to solve this. We're going to end up with a is equal to 1 from the third equation, b is equal to 1 just by substituting into the first equation, and c is equal to minus 1. That's just given there. Okay, so we can go back here, and we know what these values are. We know what a, b, and c are. So let's go back to our integration. So the integral of 2x squared minus x plus 4 all over x cubed plus 4x dx is equal to the integral, but now we know we can separate it. So a, which is 1, so we have 1 over x, b is 1, and c is minus 1. So we're going to have x minus 1 over x squared plus 4. dx. Now we can do one more separation of fractions because this fraction over here, it's better to separate it out. Okay, and then we can treat them individually. So we're going to have the integral of 1 over x plus x over x squared plus 4 minus 1 over x squared plus 4 dx. Now this middle term, it might look a bit complicated, but remember your u substitution. If we let u be the denominator, then du will be 2x. Okay, that's almost what the numerator is. So that gives us our hint. So let u be equal to x squared plus 4. du will then be 2x dx. So 1/2 du will then be x dx. Okay, So this becomes the integral of 1 over x is natural log of x. This next term becomes the integral of 1/2 times 1 over u du after doing the u substitution. And then this last one here, that's minus. This is our arctan form. Remember 1 over x squared plus a squared. That's where we use arctan. So in that case, it's going to be 1/2 arctan x over 2. Okay, because we could have written that 4 as 2 squared. So that's where we get the 2 from. Okay, now the green integral after the u substitution, that's just going to be 1/2 the natural log of u. But remember what we set u as. U was x squared plus 4. So this is going to be the natural log of x plus 1/2 the natural log of u, but we can just put that right away. X squared plus 4 minus 1/2 arctan x over 2 plus c. Okay, so just please keep in mind when you're going through these questions, you do need to know your integrals involving the natural log. So we're going to get a lot of terms like 1 over x or 1 over x plus a. Please remember that the integral of that becomes the natural log. Also, your u substitution, because sometimes we're going to have a denominator where the derivative appears in the numerator. So that's very clearly u substitution. And lastly, the integrals with 1 over x squared plus a squared, remember that those become arctan. Okay, that proof I left as a homework exercise. Okay, so just try that out. You should be getting arctan for those types of integrals. Okay, you just use one of your trig substitutions and then you can show that. However, for the assessments, please don't do the whole trig substitution every time. If you have an integral, which is 1 over x squared plus a squared, please just use the arctan formula, okay, where it's 1 over a arctan x over a. You don't have to do the whole trig substitution. Okay, so your trig substitution, that will be assessed in a separate question. Okay, then you use your trig substitution there. Well, else it just becomes too much work for something so simple. Okay, so that's it for today. I just wanted to go through 2 examples just to show each step to help you out. Tomorrow, we will be going over any last questions that you have on partial fractions and integrating rational functions. If you don't have any questions, then we will be moving on to the new section on improper integrals. So just a little preview of that. For improper integrals, can't spell today, integrals. So for improper integrals, those are integrals like this. I just want to give a quick sketch. So let's say we have something that goes off to infinity, like 1 over x squared, for example, and we want to work out this area here. Okay, the area all the way to infinity. Now, we can't just do that using a Riemann sum because we're going to have infinitely many terms going down. So we're going to be using limits instead. So something like this, integral from 0 to infinity, f of x dx. We can't just substitute infinity. That doesn't make sense. So instead, we write this using a limit. So the limit as t goes to infinity, the integral from 0 to t, f of x dx. Okay, so we're going to be looking at things like that. And the next kind of improper integral, something like this. So let's say we've got some bad behavior, like a vertical asymptote like this. However, we're still interested in what might this area be underneath. Okay, is it finite or not? Okay, so in this case, since we've got this vertical asymptote, we need to split this up at the asymptote. So if this is a, on the left-hand side, we're going to be taking the limit as x goes to a minus, and then on the other side, we have the limits as x goes to a plus. Okay, because we can't exactly evaluate at a because of the asymptote. So if we want to find the area, we need to do some sort of limit on either side. Okay. Okay, so these are the two types of improper integrals we're going to be looking at. The first case with infinite domains, and then in the second case with discontinuities. Okay, so just because there's a discontinuity doesn't mean we can't integrate it. However, we do need to be very careful with those discontinuities. Yeah, sometimes the integral does go to infinity, sometimes it's finite. Okay, so we're going to be looking at that next time. Okay, but like always, if you have any questions, please post them on the WhatsApp group, or you can email me as well. Okay, but I will see you tomorrow. Bye.